Two particles are separated by the length of a microchip, or by the width of a galaxy. Changing one particle's property instantly influences the others. This is a fundamental behavior in a universe called quantum entanglement. This interaction is so unusual to our microscopic perspective that even Albert Einstein found it initially unconvincing. I cannot seriously believe in it because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky actions at a distance. What is this spooky action, and how does it enable quantum computers to perform highly complex computations? Inside these quantum computers are qubits, the quantum version of the bit. The qubits, commonly represented as individual particles, must communicate clearly and quickly for the computer to compute. Without such communication between particles, these machines would not work much differently than classical computers. Qubits mutually influence their values, which requires quantum entanglement. This entanglement works with two separate qubits by combining their existences as a single, unified system, no matter how physically separated they may be. Two qubits contained within quantum computers require connection to have an effect on the resulting calculation. The connection is achieved by entangling their quantum states. These states are represented by 0, 1, similar to that of a classical computer. When connected, the qubits are then put into an unmeasured state, in which their quantum state could be 0 or 1. Let's entangle two qubits, A and B. We can prepare them so that their values will always be opposite. Before we measure them, each qubit exists in an undefined state, a 50% chance of being 0 or 1. Let's measure qubit A. Qubit A collapses, and its random state becomes 1. Now the fundamentals of quantum entanglement can be observed. Qubit B, regardless of its location, will then possess qubit A's opposite quantum state, 0. Qubit B collapses and reveals its state. We repeat this process and find that after measuring the qubits' states are always opposite of one another, just like how they were initially prepared. This is a fundamental occurrence in quantum entanglement. The outcomes of the entangled qubits are completely dependent on the other qubit. This is true despite that when the qubits are undetermined and then measured, their results are always random. Fun fact, wave functions, which I can describe in another video, are mathematical models that explain probabilities of a particle's result. However, when trying to make a wave function for a singular entangled particle, you fail. You can only successfully make a wave function for the entire entangled pair. But why is this important? Why utilize quantum entangled pairs in computing? It enables a processing behavior named quantum parallelism. Simply, quantum parallelism is the ability for a computer to perform multiple calculations simultaneously. In classical computing, there is no quantum entanglement. The individual bits cannot inherently utilize parallelism. To do multiple calculations at the same time, classical computers require multiple cores. In quantum computing, however, since entanglement is a fundamental component, parallelism is essential to the way the computer calculates. But how exactly does quantum parallelism work because of quantum entanglement? When qubits are in a probabilistic state of 1 or 0, they are in a superposition. In this superposition, the individual qubits themselves are able to represent two values at once. Two classical bits can store one of 4 combinations. Two qubits can represent every single combination concurrently. The computational power scales exponentially with each additional qubit. Classical computers only scale linearly, but if qubits can be in a completely probabilistic state and exist in 2 states at once, why do you need to entangle undetermined qubits? If all you have are qubits in superpositions, the individual qubits cannot influence one another. They have not formed a larger unified system. Utilizing entanglement allows a singular qubit to impact the entire qubit system. In fact, without entanglement, Every input that a quantum computer attempts to calculate will consequently provide only random results. Entanglement is what links the fates of the qubits together. When you apply a logical operation to one qubit, its results predictably propagate throughout the entire system. You aren't really running many calculations separately, you are running a singular complex calculation that represents multiple possibilities.